Welcome to the Special Purpose Integrated Circuits chapter. Previously, we have learned about op-amp circuit which we could operate as a comparator, differentiator, and adder. These circuits exist in the form of IC and one of them is LM741. A general purpose op-amp such as LM741 is a versatile and widely used device. However, some specialized IC amplifiers are available that have certain features or characteristics oriented to special applications. Most of these devices are actually derived from the basic op-amp. So, what kind of IC circuit that we will discuss today? Based on the listed objectives, we will learn and discuss 4 types of op-amp special circuits. These special circuits include the instrumentation amplifier that is used in high noise environments, the isolation amplifier that is used in high voltage and medical applications, the operation transconductance amplifier OTA that is used as a voltage to current amplifier, and the logarithmic amplifier that are used for linearizing certain types of inputs and for mathematical operations. Log amplifiers are also used in communication systems, including systems that employ fiber optics. Wow, it seems that the application side of the special circuit op-amps is widely used in the engineering field, especially electrical and electronic, which are very close to us. Now, let's learn and understand the operational of each circuit in the next slide. An instrumentation amplifier is a differential voltage gain device that amplifies the differences between the voltage existing at 2 input terminals. The main purpose of an instrumentation amplifier is to amplify small signals that may be riding on a large common mode voltages. The key characteristics are high input impedance, high common mode rejection, low output offset, and low output impedance. The basic instrumentation amplifier is an integrated circuit that internally has 3 operational amplifiers and several resistors. The voltage gain is usually set with an external resistor. A basic instrumentation amplifier is shown in figure. Op-amps A1 and A2 are non-inverting configurations that provide high input impedance and voltage gain, while op-amp A3 is used as a unity gain differential amplifier with high precision resistors that are all equal in value, where R3 is equal to R4, R5, and R6. The gain is set by a single resistor that is supplied by the user labeled as RG. This setup clearly shows that the output voltage is the closed loop gain set by RG multiplied by the voltage differences in the input. By choosing or setting the correct value of RG, we can control the voltage gain of the instrumentation amplifier by using this relationship formula, where RG is equal to 2 times R divided by ACL minus 1, where in this case, this R is actually equal to R1 and also equal to R2. Now that you have the basic idea on how an instrumentation amplifier works, let's look at a specific device. A representative device, this time is the AD622. This instrumentation amplifier is based on the design used 3 op-amps that was shown before. For the AD622, an external resistor must be used to achieve a voltage gain greater than unity as indicated in resistor RG is connected between the RG terminals, which is between pin 1 and pin number 8. RG is selected for the desired gain based on the following formula, which is RG is equal to 50.5 kilo ohm divided by AV minus 1. Notice that this formula is the same as equation in the previous slide for the 3 op-amp configuration with an external RG, where the internal resistor R1 and R2 each has a 25.25 kilo ohm value. Here is an example for you. What is the value of RG so that the gain is set to 35? Do you have the answer? Okay, easy peasy. Just put the value of 35 into the formula so that the RG is equal to 50.5 kilo ohm divided by 34 The answer will be RG is equal to 1.5 kilo ohm. Now let us examine how the gain varies with frequency for gains of 1, 10, 100 and 1000. As the curve shows, the bandwidth decreases as the gain increases. Could you find from the graph what is the bandwidth for a gain of 35? Reading from the graph, by looking at the y-axis, the bandwidth is approximately 200 kHz. Various types of transducers are used to sense temperature, strain, pressure, and other parameters in many types of applications. Instrumentation amplifiers are generally used to process the small voltages produced by a transducer and often are used in noisy industrial environments, where long cables are used to connect the transducer output to the amplifier inputs. Noise in the form of common mode signals picked up from external sources can be minimized, but not totally eliminated, by using coaxial cable in which the differential signals wire are surrounded by a mesh metal sheeting called a shield. As you know, in an electrically noisy environment, any common mode signals that are included on the signal lines are rejected because both inputs to the amplifier have the same common mode signal. However, when a shielded cable is used, there are stray capacitances distributed along its length between each signal line and the shield. Instrumentation amplifier with shield guard, as shown in the figure, is used by driving the shield with the common mode signal, so that the effects of stray capacitance are effectively cancelled. Guarding is useful in applications such as transducer interfacing and microphone preamps, where very small signals need to be transmitted. An example of specific IA with a guard output is AD522. The AD522 is a low noise instrumentation amplifier that has a data guard output which is connected to the shield as shown. The AD522 has a program gain from 1 to 1000 depending on the value of RG. The frequency response rolls off at negative 20 decibel per decade as shown in the graph. Now let's move to the next item, an isolation amplifier. It is a device that consists of two electrically isolated stages. The input stage and the output stage are separated from each other by an isolation barrier, so that a signal must be processed in order to be coupled across the isolation barrier. Some isolation amplifiers use optical coupling or transformer coupling to provide isolation between the stages. However, many modern isolation amplifiers use capacitive coupling for isolation. Each stage has separate supply voltage and ground, so that no common electrical path between them. A simplified block diagram for a typical isolation amplifier is shown in this figure. An isolation amplifier is designed to provide an electrical barrier between the input and the output in order to provide protection in applications where hazardous conditions exist. The input stage consists of an amplifier, oscillator, and modulator. In this case, the modulator uses a high-frequency square wave oscillator to modify the original signal, while the output stage consists of a demodulator and op-amp. The modulator extracts the original input signal from the modulated signal so that the original signal from the input stage is back to its original form. A typical isolation amplifier uses a high-frequency modulated carrier frequency to pass a low-frequency signal through the barrier. The ISO124 is an integrated circuit isolation amplifier. It has a voltage gain of 1 and operates on positive and negative DC supply voltage for both stages. The ISO124 is a capacitively coupled isolation amplifier that uses pulse width modulation to transmit data across the barrier. The frequency response is specified to 50 kHz, but high frequency ripple due to the pulse width modulation may be observed on the output at higher frequencies, where the output may show ripple with a high frequency sine wave input. The 3656 kg is one example of a transformer coupled isolation amplifier that uses pulse width modulation to transmit data across the barrier. The 3656 kg can have gain for both the input and the output stages. So the total amplifier gain is the product of the gain of the input and the output stages. The 3656 kg is suited for patient monitoring application such as an ECG amplifier. The manufacturer's datasheet shows the detailed connection diagram for various applications. As previously mentioned, the isolation amplifier is used in applications that require no common ground between a transducer and the processing circuit, where interfacing to sensitive equipment is required. Isolation amplifiers are common in patient monitoring applications to avoid potential shock from the monitoring equipment. Here is an example of isolation amplifier used to isolate the electrode paste on the mother from the monitor. Conventional op amps, as you know, primarily voltage amplifier in which the output voltage equals the gain times the differential input voltage. The operational transconductance amplifier OTA is a voltage to current amplifier in which the output current equals the gain times the differential input voltage. As in the case of FETs, the conductance is output current divided by input voltage. Thus, GM is equal to I out divided by V in. Like FET, the gain of amplifier with voltage control gain is written in terms of GM, where AV is equal to GM times RL. Voltage gain is controlled by this variable voltage, which is V bias. So by setting or program the output, it can be done by varying the DC voltage of V bias. The OTA adds a measure of control to circuits commonly implemented with conventional op amps. Applications for OTAs include voltage control low pass or high pass filters, voltage control waveform generators and amplifiers, modulators, comparators, and Schmitt trigger. Figure shown illustrates an OTA connected as an amplitude modulator. The voltage gain is varied by applying modulation voltage to the bias input. When a constant amplitude input signal is applied, the amplitude of the output signal will vary according to the modulation voltage of the bias input. This application known as amplitude modulator or AM. Next is lock and anti-lock amplifiers. Both are used in applications that require compression of analog input data, linearization of transducers that have exponential outputs, and analog multiplication and division. They are often used in high-frequency communication systems, including fiber optic systems for processing wide dynamic range signals. The key element in a lock amplifier is a device that exhibits a logarithmic characteristics that, when placed in the feedback loop of an op-amp, produces a logarithmic response. A diode has the characteristic in which voltage across the diode is proportional to the log of the current in the diode. Compare data for the actual diode on linear and logarithmic plots. When a diode is placed in the feedback path of an inverting op-amp, the output voltage is proportional to the log of the input voltage. The gain decreases with increasing input voltage. Therefore, the amplifier is said to compress signals. Many sensors, particularly photosensors, has a very large dynamic range outputs. Current from photodiodes can range over 5 decades. For a log amplifier with a diode, a log amp will amplify the small current from the larger current to effectively compress the data for further processing. The output voltage can be expressed by this formula, where Vout is equal to negative 0.025 times ln V in over IR R1, where IR is a constant for a given diode. You can see that the output voltage is the negative of a logarithmic function of the input voltage. The value of the output is controlled by the value of the input voltage and the value of the resistor R1. The other factor IR is a constant for a given diode. Now it's example time. Determine the output voltage for the log amplifier. Assume IR is equal to 50 nanoampere. By utilizing the given formula, Vout is equal to negative 0.025 times ln of 11 divided by 50 nanoampere times 1 kilo ohm, which gives us negative 307 millivolt. Now let's change the diode with a BJT. When a BJT is used in the feedback path, the output is referred to the ground of the base connection rather than the virtual ground. This eliminates offset and bias current error. For the BJT, the IEBO will replace IR in the equation for Vout, where Vout is equal to negative 0.025 volt times ln of Vin over IEBO times R1. Log amplifiers are available in IC form with much better performance than the basic log amp shown here. For example, a TI log 114 can operate over 8 decades from 100 picoampere to 10 milliampere and avoid temperature issue, has improved bandwidth compared to others. An anti-log amplifier is formed by connecting a transistor or diode as the input element. An anti-log amplifier produces an output proportional to the input raised to a power. In effect, this is the reverse of the log amp. The equation for Vout for basic BJT anti-log amplifier is Vout equal negative RF times I of EBO anti-log Vin over 25 millivolt, where the exponential terms was expressed by anti-log. Integrated circuits are available that can do both the log and anti-log function on the same IC. One of that is AD538, for example. It can do a variety of computations including log ratios, squaring, square roots, trigonometric function, and more. This section forward introduce a few more devices that represent basic application of the op-amp and linear integrated circuit, such as constant current source. In this type of application, if RL changes, IL will remain constant as long as VE and RI are held constant. Second is the current to voltage converter. A current to voltage converter converts a variable input current to a proportional output voltage. A specific application of this circuit is photoconductive cell is used to sense changes in light level. As the amount of light changes, the current to the photoconductive cell varies because of the cell changes in resistance. Next is the voltage to current converter, as shown in this figure. And last but not least, the peak detector. In this case, the op-amp is used as the comparator. This circuit is used to detect the peak of the input voltage and store that peak voltage on a capacitor. For example, this circuit can be used to detect and store the maximum of a voltage surge. This value can then be measured at the output with a voltmeter or recording device. Audio amplifiers are available as a complete system integrated circuit. One such device is the LM386 that can have a voltage gain from 20 to 200 set by external components. An example of an LM386 used as an audio amplifier in the last stage of a radio receiver is shown here in this figure. To summarize this chapter, let us revise this listed definition. First is instrumentation amplifier. It is an amplifier used for amplifying small signals riding on large common mode voltages. Isolation amplifier. It is an amplifier with electrically isolated internal stages. OTA or operational transconductance amplifier. It is a voltage to current amplifier. And lastly, transconductance. In an electronic device, the ratio of the output current to the input voltage is equal to transconductance. Okay, don't forget to try the quiz assigned in the MS Teams channel. If you have any question, please put forward in the respective channel. Good night and have a nice day.